Welcome to my Commodore 64 Games Memories. This is where I look at old games and some of the technical details behind them. Let's get into it. Today we have Power Drift, published by Activision in 1990. Copyright Sega. Now this was originally a Sega arcade game which used a lot of scaling and rotating graphics, so the translation of this, or the conversion of this, to the Commodore 64 was really a technical feat by Chris Butler, who coded it, and the musician Dave Lowe, if I remember correctly. So I'm going to jump straight into the game with this. We can see here on the title screen that we can find the game screen quite quickly. So the game screens are here. We can see that we've got two character sets up in the top of the ROM. One of the character sets is used for the title screen, and we've got the sprite here as well. So this game, relatively unusually, uses the memory address range at E800 and EC00. We can see here for storing the game screen and the title screen in a double buffered fashion. I mean, the double buffering is usual, but now if you look in the memory view, in the middle of the memory view we can see these green rectangles being frequently copied as the level progresses. Just below that green and yellow bar, roughly in the middle of the game. Now that means the green is being read from, and then it's updating the screens with the yellow bars down at the bottom of the memory view. Now, these green rectangles kind of indicate to me that this is a load of copies being done to render the background graphics. Now, as I'm playing the game here, if you notice in the bottom of the memory view, there's occasionally a yellow bar like that just appeared there. And this yellow bar is actually, it's difficult to notice it, but you can notice it in the corner of the eye. So if you rewind the video and have a look, or I'm going to try and get it to happen a little bit more when we're actually viewing it. Now I'm just hunting through the memory here. So yeah, we have two character sets. So the other character set, which is at F000 instead of F800 for the game, the top part of the screen we can see contains the characters, the people that are above, and the position indicator and the score and the time and everything like that. The top, 4 character rows are there for the score. So there is a split screen, and it is using both character sets. Now for space purposes, I guess Chris Butler didn't need to have extra sprite graphics, so I guess he put all of the graphics in the last bank just because he had space. I mean, usually, if I was doing this, I would have put the other character set in a different bank and used the top of the other bank, top of the screen in the other bank, to display the score panel and everything else. I probably would have tried to save space and have more sprite graphics. So the two double buffered screens is a usual way. You can see that this screen here, the second screen for the game, shows the vertical thing which comes down at the very beginning. The top of the character screen for the game on the left hand side just seems to be empty graphics, or maybe sprite graphics or something like that. Now I'm really interested about these large rectangular green blobs that are being copied. It's evidently that it's copying rectangular blobs. Now the memory view here is aligned to 256 bytes wide, a whole kind of like page, if you like. I'm going to expand this and put it down here next to the graphics map. We can also see that the what looks like the color RAM is also being updated in a chunk. So the color RAM is being written to in the memory view, along with the double buffered screens. All of these rhymes are in yellow here. The cars actually have, 4 sprites? 1, 2, 3 for the wheels and the chassis, and the 4th sprite for the person. So when you have 3 of those race winner cars, one after each other, it's 3 times 4 sprites, which is 12 sprites already, which is quite an achievement of multiplexing along with everything else that's going on the screen. And then of course with the 4th car underneath it as well, that would be 4 times 4, which is 16 sprites all being nicely multiplexed. So keep an eye out on the bottom row of characters as I'm playing through the game. There we go. It just changed. The bottom row of characters just changed as different background objects come along. And let's keep on playing. Keep an eye on the bottom row of the characters, the last character set, bottom row. I'm keeping on going along. There we go. They've changed again. So at regular intervals during the level, during the track, there seems to be like kind of like a pause. Well, not a pause, an empty area of the track where a whole bunch of characters are copied across. So what I'm going to do is that I'm going to put in a breakpoint, I think. I'm going to put a watch for a store for anywhere apart from the last 16 bytes. I don't want to map out, I don't want to trap or watch or breakpoint on stores going into the interrupt vectors, for example, if the ROMs are off. Now, the thing is about this game is that it's one single load. Although this was the disk version, it is still one single load. It was still one single load on the tape. It really is a feat of engineering to have. There we go. We have a break point that's triggered. So let's have a look. So Power Drift was actually in my list of games that I wanted to have a look at anyway, but there was a comment on my YouTube video about, I think it was the Armalyte video. Somebody requested for me to have a look at Power Drift. They wanted to know how the graphics are done, so this is why I'm looking at the Power Drift now. I've bumped it up the list. We can see here that there's a whole bunch of load and stores. Actually, it seems to be copying 4 full 256 byte pages. There's the load X for load Y, dec Y, branch on equal, and then increment 0 page addresses, the high addresses, and then decs. So yes, it's copying over a full K from 6310 to FA10. Low and high byte, remember, ordering with these indirected addresses. So yeah, at this point it seems to be copying over 400 in hex bytes, which is 1024 in decimal bytes, a full K into this area here. That's intriguing. No, the great thing, well, you can see from the game that there are no roadside objects at this particular point in time, so actually the frame would have been relatively quick to calculate. So adding in a whole bunch of extra copying, and we can see that it's actually copying an extra 77, maybe 78 bytes. Look, there's BPL branch on plus, so actually it's copying 0 to 7 in hex. So it's copying 478 bytes worth of character set data. Wow. Okay, and then it's just, it jumps back. And then if I get, there we go, bing. So it was probably copying in the character set data for the start finish line thing, right? The gantry, because the start banner is actually relatively complex in terms of characters. It's probably copied those in just so it can render it properly. Or maybe it was copying it. No, it wasn't copying in the backdrop. It was far too early. Or maybe there was another copy of backdrop data, because this backdrop, the city skyline, the clouds, and everything, that's roll left and right. There we go. See. At this point in the game, actually, it's got some billboards, but still, it seems to be doing a whole bunch of copying. Cool. So we can figure out from this that it's copying the characters from somewhere in memory, and it's actually doing just a straight memory copy. It's not doing any decompression by the looks of it. I don't see any writes going on from the memory that it was copying the character set data from. Right. So in this case, it's copying from 5820. So if we have a look, in the character sets at roughly 5820, which is inside this other bank, yeah, we can see character set data. Look, we can see a third message, we can see what looks like text, we can see all sorts of interesting stuff, all nicely laid out. And then we can see what looks like structured graphical data after that. Do you see that structure there? That is interesting. So these are the game screens with this character set. There seems to be a lot of structured data there. It's either lookup text, but we know that this area of memory is copying large rectangular green blobs, right? And these green blobs seem to be large and small that correspond to the large and small background graphics that are being drawn for the racetrack. So yeah, we seem to have a 256 wide character map of data that's, I don't know, it looks like 70 or 80 pages long, maybe even 90 pages deep rather, sorry, vertically. That's a huge chunk of memory for what looks like copying background graphics. Because the shape of the background graphics corresponds to the shape of the background graphics that we can see being drawn on the screen at that particular point in time. It's not writing to that memory where we think, or where I think that the background graphics are. It's just copying from. So if I do a check, right, let's put it in this breakpoint, storing to the character set data from where it's copying from before it goes up into the high graphics bank. So we'll just play around, we'll play the level a bit and we'll see if it breaks anywhere on a store. And I don't think it does. Look, it's just doing copies. And then yeah, these RAM copy patterns, they are almost a dead giveaway, right? But we need to validate this hypothesis. So what I'm thinking is that we can maybe dump this memory and then try and import it and actually see into like a map viewer or something like that. We could do something along those lines, because in ICU, in this version of ICU, I don't think there's an easy way of viewing different oriented map data. So yeah, I'm going to save a snapshot image. I need to remember F800. I need to also remember that rough memory address. Okay, so let's use this charpad tool. I want to import the VSF. I don't use this option very often, so this is a little bit of a learning experience for me. Oh, look. This looks like house. There we go. Look, see? You can see trees. Oh, this window is quite small. Bother, I can't adjust the window size with this window open. Okay, anyway, so you can see there that there were some trees and the houses. They look like there are houses there, but the houses seem to use a different character set. Now, this is not a surprise. We know already that the game was copying in a kilobyte plus hex 78 bytes or something like that, right? For one frame, maybe even two. So let's make this window bigger. Yeah, let's go back and do it again. I'm going to make the window, trying to remember how to use this tool now. No, I don't want to enable tiled mode. Multicolor mode is enabled. Make it easier to see, although you can see the chevrons really easily, right? And the trees are actually quite easy to see as well. The palm trees, they look like palm trees or pineapple trees, something like that. Ah yeah, this is how you change the map. Right, so let's change it to be, maybe that's not a great color. Let's try and choose some sensible multicolor colors. Maybe that. Okay. Maybe just trying to get something which looks vaguely sensible. So the game, wouldn't really change the multicolor colors unless it was between levels or something like that. I don't think. but anyway, that kind of accentuates what we're trying to look at, right? Let's change the color here so we can that's high res green and that's multicolor green. Yeah, there we go. The trees look kind of much better now, right? And the chevrons do. Now we can definitely see that the houses use a different character set. I'm not worried about that. But we can see the houses get bigger and smaller. We can see why those green rectangles were changing in size and where they were copying from, because we have this huge, great big 256 byte or character wide map sitting in memory. Now it all goes down to about whatever this coordinate here is. It looks like the structured map data, the game object data, finishes at roughly, using this character set, yeah, smaller tree, bigger tree, blah blah blah. We got some barrels there too as well, let's see. It seems to be finishing rather, if I pick the coordinate, it's probably here. So maybe 74 character rows, 75 character rows, 74 character rows tall by 256 bytes wide. If I zoom out, yeah, look, see, you can definitely see there's the lobster sign, big lobster sign, bigger lobster sign, smaller lobster. Basically, this has been laid out in such a way that the graphics pack together quite efficiently, wouldn't you say? So let's do that, and then let's do this again. There we go. So you can scroll up and down all the way through memory like this, and yeah, we can definitely see. Isn't that cool? Does look rather nice. I think we can even see the game start lift thing, which lifts you up and down, right, and then the thing drops you down. So there we go. We can extract. Now, I think if during the game, right, we could extract the different character sets for these different graphics, then that would allow us to basically re-engineer this game using its graphics, if we were so inclined. Now, you know, to be honest, I wouldn't store all of the level graphics like this in just completely expanded blocks where it does rectangular copies. To be honest, I would optimize the graphics so that it stores the minimum amount of span data. This would then mean that game objects for the level were not limited to the rectangular block copies. You can see here the block copies would be linear and therefore faster reading the data, and then storing it to the screen would be of about the same speed as doing this. So I would have done it like that, because every row where it needs to go down to the next row, there would need to be some increment to get to the next high byte. Now, yes, it uses a 256 byte wide map, so that it's just an increment, but it's an overhead, right? And doing a rectangular copy does have some inefficiency. Also, there is a slight inefficiency in the way that the graphics are packed into the memory, although there doesn't seem to be too much wasted space here. I can't help think that there would be some efficiencies in packing together the rows of data. So for those of you who are actually looking at my GitHub repository, I have some example source code for a game project called Racing Game, which actually does some of these optimizations. So it stores optimal character set packing for the game objects. It does a linear read for the game objects. And I know it's faster because you can then produce some optimized routines for when you're drawing a game object in the screen without any clipping, and then if you're wanting to clip it to the left or right hand edge of the screen, then you can. The idea being that actually game object data can be stored in cartridge ROM rather than in the Commodore 64's RAM, meaning that actually you could read in a whole lot more data and have a whole lot more complex graphics without having the Commodore 64's RAM limitation. You can all stream it from ROM instead. So here I'm just having a look at the boot for the game. Since we located where the graphics were for the character graphics for the game objects, I'm going to have a look at how the game auto boots, because why not? I've never really looked at the disk version before. Let's get the G64 file name. There we go. Okay, list 2 files with a whole bunch of sequential files, which have weird block counts. Okay, no problem. Okay, the directory view is badly linked, hence it was trying to extract those files over and over and over again by the looks of it. Also, again, not really a problem. Let's have a quick look in the hex editor. So 02A7, so it's probably doing some kind of like vector claim, but if you have a look, it's also got a sys2061. This one seems to load at 34. There's some text at the bottom, system NTSC. Really, no, but this is the PAL version. Okay. Anyway, this initial sys is interesting. It's got some code after it. I can see hex code bytes already. So this is doing a load 8,1, which puts it into that space in memory where it can probably claim vectors. What happens if I just do a load 8, which loads it into basic program memory? Look, there is the 2061. Let's have a quick disassemble. What is 2061 in decimal? Oh yeah, look. So there's this entry point for the sys. It does a whole bunch of copies, stores the stuff at 2A7, sorry, and then jumps to 2C4. Okay. So even if you load it as a basic program and then want to try and run it, it will still run the auto boot code explicitly after copying it into memory. Fantastic. So anyway, if you load it with 8,1, which loads it into the vectors, then of course it will do, as we can see here, an entry point for the code, and after running through a particular vector or something like that. I've forgotten the label file name. There we go. Right. No, I need quotes. Right. So we can see it does a set message, set fs, set nam, blah 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 blah. Okay. Fine. It's loading screen color and storing it in color RAM. Well, that's unusual. Okay. Fine. Initializing the color RAM like that is slightly unusual, because probably the first thing that the loader code does is write over it anyway, but okay, whatever. We can see here that it's just going into the standard kernel serial bus routines, blah 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 blah. After loading the labels, which adds the breakpoints, I'm going to remove them again, because I just want to very quickly run through this. You see it loaded a whole bunch of code, and now it's jumping to that whole bunch of code. There seems to be some NOPs there, probably, I don't know, but we'll see. Anyway, so yep, there we go, 334, jump 3F353, blah blah blah, usual kind of stuff. More set messages, resetting the stop vector high and low, blah blah blah. EDFF, okay, looks like it's jumping into the kernel. Power drift, TM, copyright, Sega, blah blah blah, Activision, authorized user, code, Chris Butler, music, which is probably Dave Lowe, right? System. There is some text there, but not very interesting text. Okay, fine. So probably let's hazard a guess about what this is doing. Seems to be setting up some timers and stuff like that, and interrupt controls and things. Okay. It might be obfuscation, it might be timing check to see how long the drive takes to respond. Maybe. It seems to have loaded quite a fair chunk of code, to be honest. I don't see any obvious memory write or memory execute commands either hidden in the memory forwards or backwards at the moment. But the disk loader on this was actually really annoying. It had like a a warbling sound effect that was going on as it was loading data, and actually there was a little what looked like raster interrupt move or filling the border of the screen with border color as it was loading more data, which is a really quite unusual way of displaying that you're loading data by making a really annoying wobbling effect. I mean, you know, the Nova load did it, but that was only a very short burst, and then it started playing proper music. This doesn't play proper music, it just warbles the sound effect for the whole of the game load, and also while it was loading some of the title screen. So I'm now going to think about drive code. Let's put a breakpoint in the drive memory space inside the buffers, which is where drive code would normally try and get executed from. Right, there we go, the drive code has done some stuff. D042, I don't quite remember what that does. The label names in the drive code actually correspond to the Commodore 64's address space, so ignore the label names, they're not correct. But you can have a look at the bytes to ascertain what the actual address is. 3D4 is a store accumulator, absolute to DD00, right? Anyway, D042 is load, bam, load the block allocation map. You know, I would have put code in the block allocation map and then loaded that and then executed it. Because you know where in the drive it loads the block allocation map. In fact, the drive loads the block allocation map by default anyway, so I would have just executed it. Because you know it's in drive memory, you don't have to tell it to load anything else. Look at 39A. If you rewind the video, there was some stores at 1800 which looks like a 2-bit protocol. Again, there's the title screen. You can hear this really annoying warbling sound effect as it's loading data. I mean, seriously. And the raster bar effect going, this is going down the memory, but on the left you've got the transition from black to what, middle grey or light grey or something. Middle grey. I did it once where I was depacking memory in one of my depackers, in Tusari I think it was. It was one of the standard depacking tools that I was making at the time. And of course I used my own depacker. I only used it very rarely though, because it added on a whole bunch of extra complexity while it was depacking. Oh look, this looks familiar, doesn't it? Yeah, loading serial bus with loading X with what's in the serial bus from the drive on the Commodore 64, doing a lookup table into the processor stack this time. Previously it's doing a load and then a store which signals to the drive it's ready to start receiving data. There's a whole bunch of knobs for timing. Look, it's doing a check with the raster position. If anyone has watched my previous Armalyte video, then this looks very familiar to the Armalyte level loading. It does look a bit like, it really does, doesn't it? So Armalyte had two very similar 2-bit protocols for the disk loader. One was at the beginning of the game, before the disk menu, where it loaded stuff really quickly, but with the screen off, and it didn't do any raster checking as far as I remember. During the level load, the screen was on, music was playing, but it had the raster bad line check. That's what this is doing, it's avoiding bad lines. Because the bad line timing, if you remember, disturbs the CPU timing, and for a 2-bit transfer like this, you need very precise timing between the drive and the Commodore 64 CPU. I'm writing some little subtitles there so that if anybody is not listening to the audio, then you can see the subtitles in the monitor view. When did these games come out? This one came out in 1990, right? Armalyte was in 1988, so Armalyte was first. I just took a screenshot from the previous Armalyte video just to see what the code looks like in Armalyte, rather than loading Armalyte in ICU and then getting to the same point. Look, it looks pretty similar. So the Armalyte view is on the right in the pane view. And I'm just going to try and line it up for you so you can see. We can see the 2-bit transfer, very obvious 2-bit transfer from the drive side. looks like the same number of knobs, right? This is doing a load X, and the other one is doing it with a load Y, but it doesn't really matter if X or Y is used. They're both used as an indirect addressing. Let's try and grab a better view of the code from the YouTube video. There we go, there's a wider view that's much easier to see. Oh, whoops, I left the mouse pointer at B508, look, covering load Y. Load from the serial port, load branch on plus, load raster. There's no set interrupt because interrupts are already disabled because the set interrupt flag is 1. Even the comparison with the raster position is the same, look, and the AND 6 compare to. So this code, which is later, doesn't do a load of 0 page. It does an immediate load and then a store into the serial bus. That's an optimization because the person who wrote this realized that the CIA chip for doing the serial bus stuff is going to always have the same output bits, blah blah blah. The bit pattern really doesn't change, so didn't need to pre-calculate into 0 page and store it nicely into 0 page. The code on the right does the load accumulate with $5, which, to be honest, I think is a little bit nicer. The Armalyte code is a little bit nicer, even though it's a slightly less optimal. But it's only like 1 cycle difference, right? There's not much in it. We can see, the load X or load Y, and then the OR with the indirected table. We can see that the table offsets are the same as well. 108, 110, 118. The table offsets shift up because it uses a different position into the table, offset position into the table, to get the right bits to OR together. So I think there's no doubt that the Armalyte code came first, but I'm pretty sure that whoever did the loader for Power Drift basically used the same code, just an iteration after that. So did Power Drift, whoever wrote the loader for Power Drift, did they get it from the same source as the people who wrote Armalyte? Because I know that, Dan didn't write the disk loader, the turbo disk loader for Armalyte. He borrowed it from someone else, but doesn't remember who, or doesn't remember the source of it. So, both games could have used the same source and then done their own optimizations on top of it. One or both could have got it from somebody who gave their permission to use it. I don't know, I'm just guessing here, but back in those days, games and other software did borrow, purloin, use code from other productions quite a lot. So the Armalyte code uses a lookup table as a page in memory somewhere. The Power Drift code uses unused space in the stack, but as you can see, the code is practically identical, barring very tiny tweaks and optimizations. Looking at the disassembly for the drive code, looking at the memory, I didn't see anything which indicated like a credit. That didn't look like a decompression, that looked like a descramble. The movement through memory was basically constant time. It wasn't doing copies and stuff from weird places, right? It was just a sweep all the way down through memory. There was a SID sound effect, which was probably replaying bytes. Let's get back to that position again. So here's the loader again. You see, I don't see any extra text in there that we haven't looked at already. Power Drift, yes. 89 MMA might indicate that this was originally written in 1989, maybe? PPJ... GMA 89, so maybe those are initials. Is that the end jump? I think that's the drop. I think that's the load loop with store to SID voice 1 frequency low. Why is that copying from all the way up in memory to the bottom? There's a jump here. As I said before, I don't think it's doing a decompression. The scanning through memory was far too consistent, and it's not doing readbacks or anything. It's just doing a straight read, write, swipe all the way down. But we'll investigate it a little further. Let's look back through the CPU history for the actual code that I missed. You can see here, border color, voice 1 frequency. Oh, look, you can see here, look, there's a whole bunch of EORs, and there's stores, TXA, EOR, store, PHA, blah, blah, blah. 6F5. So let's reset, rewind, warp all the way through back to that position again. 6D5. Yeah, setting up volume, sustain, release, control, frequency, running through the whole of memory from 834 all the way up until D0. So it's doing an EOR, very simple EOR, descramble the whole memory while updating the voice and border. Okay, very noisy, very flashy, doesn't really add any kind of protection really, because it's just a very, very simple, obvious, simple descramble. Doesn't seem to be doing any machine consistency checks, doesn't seem to be doing any kind of like protection check with results stored from, returned from the drive, or any kind of protection check. It doesn't touch that power drift message at the beginning of memory. It's explicitly descrambling data with a simple EOR. Now, if we compare the two memory blocks from before and after, we can see explicitly that the memory has changed. So the descramble has basically descrambled that, but the message and stuff is the same. The character set data is there. Oh look, there's the character set up at the top of memory. Actually, this would not have even been unscrambled, right? There is no complex decryption there. There is no complex decompression either. Bing, we're straight into the memory, straight into the game. Ding, ding, ding. There we are. So the disk loader wasn't anything special. I'm now having a look at the memory. This is the color RAM specifically, so I want to see, what is kind of being updated for the color RAM. So I think that's doing a toggle of a color. I don't think that's real color RAM update. I mean, it's doing some color RAM update, but it's not anything really consequential. I think it's just flashing something on the screen. Ah, look, there's the real color RAM copy for the game screen. So it's doing a copy from top down. Quite an optimized, semi-unrolled loop. A good trade-off between speed and memory usage. It seems to be doing 28 in hex, so 40 bytes in decimal for each row of the screen horizontally, going down a row at a time, doing a copy from 5.4. So the screen, we can see there, the screen view, the screen at 5400 here contains the color information, which matches up with one of the double buffered screens that is currently being calculated. And then it does this whole copy from top to bottom, probably, chasing the raster beam, so that the color copy obviously is not visible. To be honest, a color copy like this, it does take quite a long time, but you can afford to do it because the frame rate of this game is not at a full 50 or 60 frames a second. More often than not, it might be if the road is empty, but drawing all of these complicated objects using characters takes up quite a chunk of time, and the road effect would take up quite a chunk of time as well. So actually, yeah, so I'm just testing the hypothesis, or I'm going to test the hypothesis that this is where the color copy is. I'm going to put some characters at 54C7. I know that they're going to get copied to the screen, color RAM screen, right? But I just want to make sure that they appear on the game screen in the position where I expect them to. That's up at the top of memory. Maybe I want the next character row down, which is going to be the top of the tree. There we go. I'm going to there we go, that's the way the breakpoint should be. It shouldn't be at the, right, because I'm going to advance the frame, and we can see here that the top of the tree, the next rendered view, next rendered frame is slightly wrong, and that's because I put the wrong values in there, which is what I was expecting to see. Where is storing into that memory, which is the off-screen color RAM screen, and there we go, look. Oh look, the 0 page address at 14, hex 14, is then storing into 10. Ooh, look, it's doing a transparency. The branch on equal to 44C7 there is a transparency check, so it checks the incoming A and B is 6EED. That's well within that mapped, that character map space, which was 256 bytes wide by 70 odd character rows tall or high. That's well within that game object map. Transparency check. If it's transparent, hops over everything, just does a decrement Y and a branch on plus. This is definitely, almost certainly, the memory copy for the game object, trackside object plot loop. Almost certainly. A little bit above that, we can see that it's doing some arithmetic, pointer arithmetic, probably calculating the bounding box to copy or to do a transparency check with. The reason why I think it's the game objects and not the track is because it's doing a transparency check, and the game objects do have the notion of using transparent characters so that you can see behind things properly. The trees aren't just great big rectangular blocks. They're you can see behind where the space is, where the leaves aren't, and where the trunk is. Just adding a couple of labels here. Looks like it's doing some lookup table thing or something like that. Where does it look like the entry point for this code is? So this is a subroutine, obviously, because look, it's finishing with an RTS, so it's returning to somewhere. There's only one place in the entire game code, in the entire memory, where load Y with 0 page 12 in hex was actually in the code. I think the watch point not working is because it's a very early version of Vice that ICU integrates with. I'm pretty sure the watch points on 0 page work in other versions of Vice. Anyway, this is the JSR to 4, 4, 5, 6. This looks like that's the entry point. There's a store there, definitely, so it should have definitely been triggering, right? Anyway, I'm not going to put too much effort into trying to decode the precise algorithm behind the game object rendering. I think, if I get rid of that JSR, right, 4456 is definitely object draw. Adding a label for it. But I think if I get rid of the JSR and then view what happens in the game, let's do that. So, best way of getting rid of the JSR is to use the absolute bit instruction, I think. So JSR becomes bit object draw, so it knocks it out basically. It doesn't do anything, it has no consequences really. There we go, we can see that the game now does not have any left-hand trackside objects. The objects on the right-hand side are still there. How funny. Okay, but the game seems to be perfectly happy not rendering any left-hand side track objects. Right? So if I put it back to JSR and then go back, the trees appear as kind of expected. Fantastic, right? Very nice. So we know how the game objects work. We know that during the game it copies in multiple chunks of character set data. That green bar there is green and yellow bar 5563, which corresponds with the color RAM copy of the screen data, right? So we know that the code is updating that. So we've kind of figured out that part of the game. So we can see here that there's some stores into the sprites, what looks like a multiplexer. Let's get the old C64 debug GUI out. You could see actually there that it's got the Tusari 2 cartridge attached, which is something that I'm developing in the background. I don't want that attached. I want to load Power Drift. So let's go back, load the game, Control P, there we go, let's walk through the load. Not really interested in using the debugger to look at the loader, we already looked at that. What I am interested in is seeing the extent of sprite multiplexing that's going on. So the little cross-hatched background to the racer images that you can see across the top of the screen, the background is actually a sprite. We can see the red box around that sprite. We can see where the sprites are on the screen. There's currently 1, 2, 3, 4, 5, 6, 7-ish roughly on the screen. There seems to be a lot more hidden away in the borders, which we can't see. You know, to save a few cycles, I would have turned off the sprites and then turned them back on again, because you want as much processing time as you possibly can get, right? We'll live with it. It's only a few cycles on the scan lines where the sprites are activated, but you know, still cycles are cycles. So when the racing cars come on screen, you know, we've got 4 sprites for the main racing car. When the opposing players are also large and near to you, or near to the screen, or near to the camera rather, they also take up 3 to 4 sprites. So there is definitely a bit of sprite multiplexing going on. Turbocharge, actually, which was also by Chris Butler, right, I think has a much better, it seems to be a better, or the multiplexer on that seems to be a lot better exercise. During the game on this, you know, on Turbocharge you could fire weapons and stuff, and there were helicopters and stuff that came down across the top of the screen. In this, there aren't. But you know, actually, so here we go, the end of the game. So I've got the 4 sprites for my car, and then 4 sprites for each of the first, second, and third place cars. So that's, you know, 12, 16 multiplex sprites plus the crosshatch 17. Here you can see, you know, the start and the lights were actually sprites too. So, you know, there is a bit of multiplexing going on here. It's a fairly decent amount of multiplexing considering what else is going on the screen. The C64 debugger as well shows the character set being updated actually, you know, quite often sometimes as the level progresses. It flicked twice there in quite quick succession. So I think we'll leave it there for this technical deep dive into Commodore 64 Power Drift from 1990. Thank you very much for watching. If you like these kind of technical deep dive videos, then please consider liking or subscribing to this channel, and or leaving a comment in the comments section below. I really do love hearing feedback from people. Thank you, take care, and have a great day wherever you are.